For section 9.7, we're going to be working on solving systems that involve quadratic equations. This is very similar to what we did when we solved systems of linear equations. And it calls upon the zero product property, which we've already worked with in solving quadratic functions. So remember, when we're talking about substitution, which is one of the methods that we would use to solve a system, we would solve one of the equations for one of the variables, substitute the expression from step 1 into the other equation, and solve for the other variable. Then we take that value and substitute it back into the original equation. So, as an example, this right here has already been solved for y. Y is equal to 4x minus 6. I would then substitute that into the other equation in place of y. Then I now have a quadratic function, and I'm going to work on solving my quadratic function. So I want to put everything on one side of the equation and make it equal 0. And I want my leading coefficient to be positive, so I'm going to add x squared to either side. And I'm going to subtract 4x. 4x minus 4x is nothing. And I'm going to add 2. So I'm going to have x squared minus 4 is equal to 0. If I want to go ahead and solve this, I'm going to factor my quadratic function. I see that this is the difference of two squares. So it will be factored to be x plus 2 times x minus 2. And from these factors, I know that my solutions would be 2 and negative 2. Okay, so that's what I found so far. Now, and what that means in terms of my solutions is I have ordered pairs. I have an x value of negative 2 in one and a value of 2 in the other. And now I want to take these solutions and substitute them back into this other equation in place of x. So when I substitute 2 in, I'll have y is equal to 8 minus 6, which is equal to 2. So when x was 2, y was 2. And when I substitute in negative 2, y would be equal to negative 8 minus 6, which would be negative 14, and that would go over here. Okay, so similar to what we've done before in terms of linear systems, and also calling upon what we've learned in terms of solving quadratic functions. The difference is in a linear system I'd get a single point, because two lines can only intersect in a single point. But in this case, a line and a quadratic function can intercept in 2 points. Okay, so when we think about this, when I'm graphing, the graphs intersect at each solution of the system, which is what we had with linear systems. And let's take a look at how that looks. So when I have a quadratic and a linear, they cannot hit at all. There'd be no solution. I could have a tangent line to the parabola, and that would intersect in 1 point. That would be one solution. Or like the problem we just did, 2 solutions. Okay, if I wanted to use a graphing calculator to solve a system, I would probably want to go ahead and pull up my Desmos graphing calculator. And I'm going to take my equations and I'm going to put them into my Desmos graphing calculator. So I'm going to have y is equal to negative 3x plus 5. Y is equal to negative 3x plus 5. And there's my line. And then my others is 4x squared plus 5x minus 7. So y is equal to 4x squared plus 5x minus 7. And now you can see that we intersect at 2 different points. If I look at this point where we intersect at 1, 2, and at this point, not so tight, or negative 3, 14. So 1, 2, and negative 3, 14. And if we wanted to check those, so 1, 2, and negative 3, 14. If I wanted to check those, I'd plug them into these other equations. 2 is equal to negative 3 times 1 plus 5. Well, that's true. And if I plug it in up here, 2 would be equal to 4 times 1 squared plus 5 times 1 minus 7. So 2 would be equal to 4 plus 5 minus 7, and that's accurate. Okay, so this one checks out. If I wanted to put that, try the other solution, 14, 4 times negative 3 squared plus 5 times negative 3 minus 7. So 14 would be equal to 4 times 9 minus 15 minus 7. So 14 would be equal to 36 minus 15 minus 7. So 14 would be equal to 21 minus 7, and that is true. And if I plug it into the other equation, 14 would be equal to negative 3 times negative 3 plus 5, which is 9 plus 5. And that also checks out. Okay, so I certainly recommend if you're using a graphing tool like that to solve that you double check your answers like I just did. Solve an equation using a system. So what we could do with this particular item, if you go back to what we did with substitution, I could say this is 2x squared plus 4x is equal to y, and I could get 2x plus 4 is equal to y. And now this would be a linear system. I could graph these, or I could just go ahead and solve the original by continuing on. So I could take these either way. I could put this back up over here. If I go ahead and do this, 2x squared, if I subtract 2x, I'll have plus 2x. If I subtract 4, I'll have minus 4. If I factor a 2 out of everything, I'll have x squared plus x minus 2. This is going to factor to be x plus 2 times x minus 1. And my solutions will be negative 2 and 1. Okay, if I went ahead and plugged back in to find the y value, so again, negative 2 and 1. If I plug back in to find the y value, I'll have 2 times negative 2 plus 4 equals y. So negative 4 plus 4 is equal to 0. Right? And if we plug the 1 in, 2 times 1 plus 4 is equal to y. Y is equal to 6. Okay, so that's a possibility. If I were specifically solving this equation, then let's not even go there. A lot of cleanup to do in this one. Working on solving a multi-step problem, we've got this scenario. We're doing practice. I hit a baseball toward a gym, which is 240 feet away. So let's sort of think about what that might look like. The gym would be over here, and I'm over here, and I hit a baseball, and it's going toward the gym. Right? The path of the baseball after it is hit is modeled by this equation. Y is equal to negative 0.004x squared plus x plus 3. And then there's a roof on this gym that travels this way. Right? The gym again is 240 feet away. And then the roof comes in here. And its equation is y is equal to negative 2/3 x minus 120. Okay, so the wall of the gym is here. And the roof only exists between 240 feet and 320 feet. So this is the other side, and we've got no overhang here. Okay, so now what we want to see, right, and we also know that my wall is 40 feet high, so it's got to be between 0 and 40. Does the baseball hit the roof of the gym? Well, what we can do is we can go ahead and look at this scenario and see what's going to happen. So if I write a system of two equations for the baseball and the roof, then I'm just going to pull those two equations. So 0.004x squared plus x plus 3 is 1. And the other one was y is equal to 2/3 x and minus 120. And if I wanted to go ahead and solve this through, I could find out where the ball intersects. But in this case, what we wanted to do is graph both of them. And you see here's the graph of the ball's path, here's the graph of the roof, and you see their intersecting point is here where the roof doesn't exist. Okay, so it's at 220 feet, but the roof doesn't start until 240. Okay, so I can tell that the ball does not hit the roof. It does look like the ball probably hits the wall. That would be a different sort of question. If I looked for the intersecting point for the ball and the wall, that would be y is equal to negative 0.004x squared plus x plus 3. And the wall is x is equal to 240. If I go ahead and plug that in and solve the system, y is equal to negative 0.004 times 240 squared plus 240 plus 3, which is, that's 243. Okay, so if I go ahead and whip out a calculator, I'm going to take 240 and I'm going to square it. I'm going to multiply it times 0.004 in the negative, and that's negative 230 plus 243, 12.6. So it does hit the wall, 12.6 feet off the ground. Okay, so that's working with linear systems that involve, or sorry, not linear systems, but systems that involve quadratic functions.